In the last lecture we discussed about different kinds of loads as applied to offshore structures. We started with wind load, we discussed wave load, we discussed current loads, we also discussed tidal forces, we also discussed ice or snow load or impact load, we also discussed earthquake load, we also discussed load indirectly caused because of marine growth. So, wind load depends on projected area and surface terrain. Wave load has many complications. You have got to define the sea state first. There are many theories available to design or define the sea state. You can use simple Airy's linear wave theory, or you can use higher order wave theories to define the sea state. The moment the sea state is defined and identified, you will find out u dot, v dot, u double dot, v double dot, which are water particle kinematics generated because of the sea state. Then you will use Morrison equation to compute the forces on any individual member. Current will quantify the variation in the forces. The force or the wave elevation may increase. Tidal will include the submerged volume of the body, which will affect the buoyancy force which you want to compute. Impact load will cause local stresses on the member, so we should estimate them. Earthquake loads are considered as part of the environmental load in offshore structures. Marine growth increases CD because of roughness, which will increase the force because of CD increase. It will improve the diameter, which will cause mass, which will increase the inertia force in the member. It will also increase the submerged volume and therefore the buoyancy force. So, marine growth has got indirect effects on structural members. So, in the last lectures we have discussed about different types of offshore platforms, their structural action. I can also group them depending upon one, their structural form, two, depending upon at water depth where they are fixed, and three, of course, depending upon the functionality. For example, FPS, FPSO, FSO, etc. Depending upon the functionality also I can change. But all these loads what you saw, environmental loads, are common to all these groups of structures. There is no isolation or there is no exemption of these forces acting on any one of the group. It means I do not select a form or a type of structure of an offshore platform to avoid any kind of forces. Okay, this is a very interesting statement. Generally, if you want to avoid any specific type of action on a specific component or any specific form of a member, you design the structural system like that, whereas in offshore structures the form selection does not depend on isolation or avoidance of any of these forces. All of these forces will be predominantly present and will act on all types of offshore and coastal structures. Okay. Now, importantly, the moment I say action of forces on structures, we will talk about dynamic loading. What is a dynamic loading? when we will say the loading is dynamic in nature. One, it is time varying. It means its magnitude, point of application, direction of application, all may vary as a function of time. So, when you have a force which is time variant, then the structural response to this force or these forces will also be a function of time. The moment I understand the structural response can be a function of time, I can divide this into two classifications. One is what we call deterministic approach, other is what I call non-deterministic approach. So, remember I am classifying the response to these forces as deterministic and non-deterministic. We already understand both of them are a function of time. Why? Because the structural response will remain a function of time, because the loading applied on the structure is a function of time. So, though they are function of time, still I can classify them as deterministic and non-deterministic in terms of its approach only. Okay. What is then deterministic approach? If the time variant of the force is completely known. What do you understand with the time variant of the force is completely known? It means you know the full time history of the loading. I can give an example. Let us say I have a time history of the loading as shown here. This is time, maybe this is magnitude of the load, and it varies. You know the complete quantified variation of this magnitude at any instant of time for the full history, which is applied as a function of time on the structure whose response is also a function of time. Now, what is the difference between the loading which looks like random in my picture, but I still call this as deterministic, because it looks like random variation. Now, though it is vibration or oscillation, oscillatory, as long as the full time history is known to me, I call this loading as not a random loading, but a different name which is called prescribed dynamic loading. So, I do not call this a random load, I call this as prescribed dynamic load, because the full dynamic loading or the full time history of the loading is known to me. Okay. Once I have this prescribed dynamic loading, then the analysis what you do, to find out the action or the response of the structure for this loading will also be then deterministic. It means you will have a closed form answer of the response, that is why I call this as deterministic. In general term, deterministic means known, non-deterministic means unknown. In general terms, structures determinate, the reactions of the structural support system are known to me using the standard set of equilibrium equations. Indeterminate, some of them are not known to me, with the help of standard equations I have to solve them using some techniques. So, deterministic is related to knowledge of knownness of the time history. Now, one can wonder why the response of a structural system on prescribed dynamic loading will become deterministic. The answer is very simple. Since the force history is completely prescribed and known to me, the response corresponding to this history will also be known to me. Okay? Remember, importantly, the force varies with time, the response will also vary with time, but still I call them as deterministic because I know the full variation completely. Okay, that is why I call this as prescribed dynamic loading, or the analysis is called deterministic approach. Now, there are many advantages of doing a deterministic analysis. Number one, for example, let us look at the responses of the structural system encountered by these forces. What would be the common responses what we want to know from a structural system under these kinds of loads? Can you name few of them? What are those responses which you will be interested to know?
Deflection, bending moment.
Okay, let us start with simple. I want to know the stress sigma. I want to know, for example, the bending moment, maybe m, etc. Okay. Now, all of these values are now completely known, and interestingly one can be derived from the other. For example, if you know stress, I can find the, if you know the bending moment, I can find the bending stress, and so on. If you know the deflection, I can find. So, all of them are related. I can derive the secondary components from this analysis. Okay. So, deterministic approach has one great advantage: you may not have to arrive at all the values. If you find some of them can be determined or derived from the previous values, you can keep on doing that. Okay. This is considered as one of the advantage of deterministic approach. You may wonder, sir, why I am calling this as a deterministic approach, why not deterministic method? Do you have any answer for this? Why I am calling this a deterministic approach, why not method? Does it look like a method or as an approach? Sorry?
We are assuming that the response is deterministic.
No, we are not assuming the response determinant. We are estimating the response time history, which is completely known to me.
Particular algorithm to analyze.
So, since you do not have a particular algorithm, you call this as an approach, is it not? Is it so, or it is not a method? What is the difference between method and an approach? Method is a solution technique, approach is devising that solution technique. Say, I am looking at this problem as if it is a closed form problem. I may look at the same problem as if it is a random variable problem. Okay, it is only my view, therefore it is not a method, it is my view. I am looking at this as a closed form problem. Okay. If I look at this problem as a closed form problem, the advantages are any derivable values can be worked out successfully. So, the analysis is slightly faster, okay, it is faster. It is also dynamic analysis. Why? Why it is a dynamic analysis? Yeah, you have a time varying content present in this, which is one of the important component of dynamic analysis. It is a dynamic analysis, right, but the approach is deterministic. The structure may not be determinate, understand the terminology very carefully. Structure may be indeterminate, the approach is deterministic because it is my view, I am looking at this problem as a closed form solution. If you look at this problem as a closed form approach, then the advantages are I can derive. You may wonder why this is called as a great advantage. Why I am calling them as derivable quantities as advantages in an analysis? Any answer?
From that we can design the structure.
Fine, but why I am calling them as, what you are answering is why I want them to derive. Agreed, because I want to design, I need to know the bending moment or I need to know the bending stress. If you know the bending moment, I can find the bending stress if you know the structural characteristics. Fine, what you are answering is why I want to know them. What I am asking is why I am calling them as derived quantities, or what are advantages of this. In any method of analysis, you will not find all of them instantaneously available. Tell me any one method of analysis where you get all the structural unknown quantities at one shot, you will not get. No method exists of that nature. You will get one set of values first, the second set can be derived from the one. Can you give me an example of any one method of analysis? Okay, slope deflection method applied to statistical response method techniques, okay, but slope deflection will give you a slope and deflection, from that you can keep on deriving the fixed end moments or the reactions and the supports. Okay, so first phase of values or set of values will be what we will obtain from the analysis, remaining all will be derived from that. Okay, so deterministic approach will help you to permit you to do this kind of derivability quantities easily. Therefore, the structural analysis or the dynamic analysis forming this approach is simple and easy, okay, but the complexity is related to defining f of t and defining x of t from f of t exist, okay, these complexities are still there. So, what does it mean is all time variant responses you obtain may not be obtained from non-deterministic methods, okay, just because you saw a x of t as a response function for an f of t on a structural system, you may not clearly admit that what method you have followed is deterministic, okay. Remember, very interestingly, in this whole discussion we never spoke about the quantitative description of the structure, whether it is indeterminate or determinate, that is immaterial in this argument, okay, it is only a methodology or a way, right. Then we will talk about what is non-deterministic approach. What do we do here? Now, in non-deterministic approach, time variant loading is not fully known. Now, there is a question here, there is a confusion here. If that load history is not known, how to do my analysis? What I mean to say is, in a given window, you pick up any one of your choice and do the analysis. You do not know what is the time history of the full stretch, it is not fully known. I am not saying it is not known at all. If you do not know this, you will not do the analysis at all. It is not completely known. Okay. So, we call such kind of loading as random loading. Now, there is a very interesting terminology here, random. This is very confusing. There are two things associated with randomness. People think random loading is the load which I do not know, it is not correct, or people may say the random loading is one which keeps on varying, I do not know the variation. That is not the right terminology of understanding random loading. Even a random number has a specific designated value, it does not change. From an interval of 0 to 2 pi, a number of let us say 3.157 or 2.102, which lies in this brace of 0 to 10 is a random number, that value of the number or the magnitude of the force does not change. Then why it is called random? Because if it has got a definite value, I should not call this random. I am calling this because I do not know that guess actually. I do not know the value, I am guessing that value in a given set of 0 to 2 pi. That is why randomness comes from the choice of you selecting the load. It means the load is random because you are selecting a window where you are going to the analysis, and that window may vary between A, B, C, D analysts. Whereas this problem does not occur in a prescribed dynamic loading, because there is a full complete loading history available to you. Anybody does the analysis has to follow the time history of the total, whereas in this case it is not so. So, random loading is what we say, it is not fully known, it is not a prescribed loading. In such cases your response will also have the randomness in its representation. The moment I say randomness coming into representation, then I look for statistical content of this. I do not look for the absolute value of this, I am looking for the statistical content of this. I am not looking for the response of let us say x of t, I will not look for the response of x of t, I will look for the mean, the standard deviation and the variance as the first level values of the response. Look at the statistical content of this. Depending upon the statistical content of this, I can also try to extrapolate the distributed value of this as a property of distribution of this. Okay. So, I do a statistical content of the response. Now, one of the responses let us say displacement or deflection, y of t or x of t. From the displacement or deflection, I want to derive an additional value like rotation, or from the displacement I want to find deflection, I know I want to find the bending stress. Let us say I want to check the bending stress, I want to derive a quantity from the displacement. If you want to do that, all the derivable phase of values cannot be done in this method. So, this method will impose a penalty on you, saying every quantity requested by you should be done in the same fashion as you did for the first quantity. So, this method is computationally expensive. This method becomes computationally expensive. You cannot derive a quantity from an existing quantity in this case. Is that clear? So, that will be the fundamental difference between the non-deterministic approach of dynamic analysis to deterministic approach of dynamic analysis. Remember one important content here, both of them talk about time variance of the response, because the loading is time variant. It is the method by which you are approaching the problem. Is that clear? whatever complexities exist in the system, whatever complexities exist in defining f of t of the loading, whatever randomness exists and uncertainty exists in randomness of the loading prescription, all will remain there in both the methods or both the approaches, there is no doubt. So this method is stated as computationally expensive, whereas the earlier one is not as computationally expensive as this method. Okay, there are two different techniques or approaches by which we do dynamic analysis. Now once I start understanding the dynamic analysis, then I must also look into the other characteristic of dynamic analysis, which is inertia force. To look at that, I must speak about the mass concentration. In a given system, I would put it as mass discretization, because I am going to be keen to understand how do I study the inertia force effects on dynamic analysis. So when I talk about mass discretization, there are two methods here again. I can lump the mass at any point of a choice. I can also distribute the mass continuously over the entire length of the member. Okay, both ways I can do. This is again a deviation here. I can do both ways. I can lump the mass at a specific point, I can distribute the mass continuously for the entire member. So if you look at the comparison quickly, this will be simple, this is complex. This is commonly followed, this is not commonly followed. Both are dynamic analysis, okay, talking about the mass. The moment I speak about mass, then where to lump this mass? Because I am interested to follow a easy path, I want to do my analysis simple, though I want to claim this is a dynamic analysis, I follow this path, lumped mass system. When I follow this path of lumping the mass at a specific location, where will I lump them? That is important, okay. Now you have to lump them at places where you are identifying what we call degrees of freedom. Then what are degrees of freedom? What do you understand by degree of freedom? Now this is a very common confusing term in structural analysis itself. Let us talk about this. The degrees of freedom what you talk in dynamic analysis are different from the degrees of freedom what you talk in structural analysis. I can give an example. As we understand that most of us will understand or will know structural analysis basics. Let us say I have a hinged support, a support on roller, a support which is fixed. I can categorically say from these kinds of supports whether my structural system is statically determinate or indeterminate. To understand this, I also define degrees of freedom in the analysis. For example, support A, what are the degrees of freedom support A has? It has got 3 degrees of freedom: vertical translation VA, horizontal translation HA, and a moment or a rotational translation M. These are also degrees of freedom for joint A in a given member AB. Similarly, this will have again vertical, horizontal and rotation, but the rotation will be set to 0 in this case because it cannot. So, now I will say the degrees of freedom based on this system will be 1, 2, 3, 4, 5 or 5 are existing. I will have 3 equations of equilibrium. I can call this as statically indeterminate to a second order if I include the axial deformation in the member. If we exclude the axial deformation in the member, then the degree of indeterminacy will be different. So, here the degrees of freedom depends on where the support wants to move. So, it is related to displacement or action on the support. Okay. It can be either external or internal. It can be an action or it can be a reaction. One is called static, other is called kinematic. We can add them together to find total degree of indeterminacy. So, while defining the indeterminacy in a given structural system which is based on forces or internal reaction, we also define degrees of freedom in a given member. Okay. Now, the degrees of freedom what we talk about dynamic analysis is different from what we are talking about here, because in dynamic analysis degrees of freedom have a link with lumping of mass, whereas here I never spoke about mass in identifying this V A, H A and M A, never. Okay. So, if I understand this, then let us define quickly what do we understand by degree of freedom. Degree of freedom classically defined as the number of independent displacements of a system that is or that are necessary to represent the effect of inertia force in the system. I just now said that the degree of freedom is linked with mass. That comes from here, because mass is associated with inertia. Can I understand this in a very crude manner, saying wherever a mass is lumped, that is considered as degree of freedom? For example, I lump the mass in 3 places, the system will have 3 degrees of freedom. If I lump the mass at 10 places, structure will have 10 degrees of freedom. It means, since degree of freedom is related to representation of significant inertia force on a given system, can I crudely understand that it is the number of points where the mass is lumped. So, on the other hand, if the mass is continuous, the system will have infinite degrees of freedom. If the mass is lumped at discrete points in a given structural system, those number of points you count and understand that as degrees of freedom, but there is a catch here. You cannot associate degrees of freedom with the points where the mass is lumped. It is to represent the motion or the inertia force of the mass in terms of its displacement. It is not only the point where the mass is lumped, it are all those freedoms where the mass would like to move. I can give a very classical example here. Let us take for example a tensionless platform. These are column members, these are pontoons, this is my water level, you have a top deck and I am having all drilling etc., all these things on the top. I am going to hold this structure down using teethers or tendons, or people who have forgotten, cables. So, they will be always in tension. How to mark tension? It has got to pull the joint, we already said that in the one of the lectures. T naught, this 0 represents initial tension given to the structural system. Why initial tension is to be given? Because the buoyancy force exceeds weight in the design. So, when I try to offload this, the buoyancy will try to push the structure up automatically in a very phenomenal way. I want to hold it down, I ballast them, the structure will sink or will get a draft, connect them, deballast them, that ballast force will be transferred to tension in the teethers. That is how I install a TLP. Okay. Now, interestingly, the pontoons and the columns and the hull top side all have a specific mass, because all of them have a cross sectional dimension, they have a density of the material, they have a volume, therefore mass is there. I presume that the entire mass is lumped at a specific point, some magic point which I have arrived by some calculation. There are methods to do this, but since I do not know the method right now as a student, I pick up any point. For example, in an interview, somebody said it is an IAS interview. So, the person was sitting and the board was examining him, and he answered all the questions. He is an IAS topper from Kerala, he answered all the questions. Then one of the board members said, Mr. X, I have got one last question to you, please answer this question. He said, okay, fine, I will answer this. He was sitting on a table of an elliptical shape which is open ended, he is sitting here, they are sitting around. The person, one of the gentlemen asked, can you tell me where is the center of mass of this table? He just pointed his finger here and start walking out. The person said, no, this is wrong answer, the mass is not here. He said that was the last question. So, he cannot ask a second question to me. So, I can always select this magic point as an IAS fellow did, saying that this is my magic point where my mass is lumped. Now, the question what is troubling me is, will TLP have 1 degree of freedom? Because there is only one mass. If you crudely understand that degree of freedom is the number of points where the mass is lumped, then this should have only 1 degree of freedom. But TLP has 6 degrees of freedom. It means the mass has a liberty to move along x, to move along y, to move along z, to rotate about x, to rotate about y, rotate about z. There are specific names given in the literature which we have discussed in the previous lectures. So, it is the number of independent displacements, there is no coupling between these two, independent displacements of the mass point, because I am talking about the inertia effect of the structure. So, it cannot be crudely understood as the number of mass points or the lumped mass points where it is. Therefore, if you have got a system which has got continuous mass distribution, the degree of freedom cannot be infinite, because for all those mass points of the continuous system, I will always discuss and note the independent coordinates or the displacement coordinates where the mass would like to move. Is that clear? So, the number of points where the mass is lumped may not be same as that of the degrees of freedom of a system. We can also give another example where, to understand the independent term here. Now, I have a triceratop which is a new generation structure. As I said, offshore structural systems are not function driven, they are form driven. I select a form which should remain innovative, which should alleviate the forces coming on the structural system by way of arrangement of the members, by way of holding the member in C, or by way of assembling them so that they attract the minimum forces encountered by the environment. So, I have a triceratop. So, Triceratop has a top hull and it is having a ball joint then a BLS which is resting below and then teethers. So, these are what we call as buoyant leg structures. This is a top side hull, maybe a crude way of drawing a hull. These are ball joints. And of course, these are teethers, okay. Tendons are teethers. They are not cables, they are not wires. Okay. Let us quickly look at how do I define the degrees of freedom for this problem, because now I have got a BLS here. The BLS will have some mass. I will lump this mass at a magic number here, a magic coordinate here. Okay. Now I want to take the advantage of providing a ball joint in this connection. If this advantage of ball joint is not seen in the design, I may not have it here at all. I can have a structure like this. So, provision of the ball joint is a structural innovation in the form which will make or help the structure to reduce the forces coming from the environment. So, what is the advantage by providing a ball joint here? The advantage is that the ball joint will not pass the rotation from the substructure to superstructure. It will only filter the rotation, but it will pass the translations. So, if I have got 6 degrees of freedom here, all the 6 will not go here, only 3 will be there. So, those 3 which I have here as displacements will be independent of this. Will be independent of this. So, independent displacement components will define the degrees of freedom. It is not the mass where they are lumped. Is this clear? So, the degree of freedom explanation is different in dynamic perspective compared to static analysis of structures. There we talk about forces and actions or reactions of a given member. We never bother about the mass lumping there, but here we talk about displacements which will have effect of the inertia force on the system. When I say inertia, I will talk about mass. When I say mass, I have 2 systems, lumped and continuous or discretization of mass procedure. So, I cannot call a degree of freedom as a definition of the points where the mass is lumped. Okay. So, it is actually the displacements. What is the commonness between the degree of freedom in dynamic analysis and the degree of freedom compared to the static analysis? If there is no commonness, then the name should not be common. Okay. There should be some commonness. What is the commonness? There are 2 things which are common. One, the degree of freedom what we explain in static analysis or structural analysis also talking about independent displacements, and it talks about displacements, maybe translational, maybe rotational. What is not spoken in that is the inertia component addressed the displacements. That is the difference here. So, this gives a very interesting sense. Even if you have a platform, where the mass is lumped at 2 points or where the mass is lumped at 1 point, though it has got 6 and has got 9 degrees of freedom, but as long as the material is paper which has no mass, I may not do a dynamic analysis for this. So, that is a very important component here. I must have significant effect of inertia on the system, otherwise I will not do a dynamic analysis. So, degree of freedom explains all these complexities in a very simple statement, saying that look at the independent displacements where mass is lumped, look also for the significant contribution of inertia at these points. So, there is no point in doing all these exercises if your material does not predominantly show an inertia force. Now, the question comes, why we talk about inertia force in dynamics? Why importance of inertia is predominantly high? Sorry? So, it is coupled with the acceleration term. So, mass and acceleration will give me the inertia force, that is fine. So, why not any other term? For example, stiffness is coupled with displacement, that is also a derivative of acceleration. What poor thing the displacement has done, so that people talk only about the inertia force. Why inertia is important in dynamic analysis? That is a very interesting question, is it not? We must know this.
Inertia and stiffness is what leads to it.
What it tries to say is the coupling effect between the inertia and stiffness is very least, therefore we either talk about inertia or stiffness.
The play between these two terms will actually lead to something called resonance. If there is one part only present, suppose this.
In fact, you may be right, but I am sorry, I am not able to understand. You may be right, but I cannot understand what you are trying to say. My question is very simple, why we focus inertia in dynamic analysis? Why not displacement velocity? Of course, they are all derivatives, they are connected. Why we do not bother about them? Sorry?
Natural frequency.
Very good. We are talking about one of the important dynamic characteristics of a system, which is frequency of vibration. Frequency of vibration is related to mass, and mass is indirectly connected to inertia. So, degree of freedom is related to inertia force represented significantly on any point of a choice. It is not the point where the mass is lumped. So, we are talking about ultimately the frequency of vibration, a vibration characteristic of a given system under the given loading. Okay. So, we worry about mass. Now, there is a very critical question here. When we talk about inertia, can I replace this term as acceleration components? Why I am talking about displacement? Let us say I can always say independent acceleration components of a given structure, because we are talking about inertia, inertia is mass, mass is acceleration. So, can I replace this? Why? I cannot replace this. So, we close here, right? Think about it.